Welcome to the PluTech channel. Today we have a topic to discuss about the Apple study that reveals the flaws in LLMs. Don't miss the chance to join us and share your opinions with us. In recent years, companies like OpenAI and Google have been touting advanced reasoning as a cornerstone of cutting-edge AI models. The promise is that these AIs can replicate logical processes in ways that closely resemble human reasoning, but new research from 6 Apple engineers puts that ambition under scrutiny. The study finds that the mathematical reasoning capabilities of language models, LLMs, are extremely fragile and inconsistent when faced with even minor changes to standardized mathematical benchmarks, suggesting that their performance may be less robust than it appears. These findings support the theory that LLMs, when using probabilistic pattern matching, fail to reliably grasp formal concepts. The researchers argue that in practice, these AIs do not perform genuine logical reasoning. Instead, they reproduce sequences of reasoning that they have identified in their training data. In other words, the models are closer to pattern mimics than to true logical thinkers, a limitation that could compromise their usefulness in complex mathematical contexts. In the paper, GSM Symbolic, Understanding the Limitations of Mathematical Reasoning in Large Language Models, the researchers explore the limitations of these models by testing the GSM-8K set, a benchmark of over 8,000 high school math problems. However, the Apple team did something different. They modified part of the benchmark to create GSM Symbolic, where the problem names and numbers were randomly changed. For example, a question about Sophie buying 31 blocks was changed to Bill buying 19 blocks. While these changes didn't change the underlying mathematical logic, they did reveal how these small variations affect the model's performance. The approach avoids the problem of data contamination that occurs when standardized questions are incorporated into AI training. In theory, since the difficulty of the problems remains the same, the models should maintain the same level of performance on GSM Symbolic. However, in practice, the performance of the tested LLMs dropped dramatically, with reductions ranging from 0.3% to 9.2% depending on the model. Furthermore, accuracy was inconsistent across multiple runs. In some cases, there were variations of up to 15% between the best and worst attempts, even when the model was tested on problems that were identical except for minor changes in names or numbers. These inconsistencies suggest that LLMs do not operate with formal, structured reasoning, but instead compare patterns superficially. Changing numbers, for example, was shown to be more detrimental to performance than changing names, indicating that the models rely heavily on specific patterns memorized during training. As the researchers point out, the necessary reasoning steps remain the same, but the variable results indicate that the AI is closer to a pattern recognition machine than a logic-solving tool. Still, not all results were catastrophic. ChatGPT-4, for example, only saw a marginal drop, going from 95.2% accuracy on GSM-8K to 94.9% accuracy on GSM Symbolic, a small but notable difference. However, when the researchers added additional layers of logical reasoning or introduced irrelevant information into the problems, the performance of many models dropped dramatically. When testing a new benchmark called GSM NoOp, which includes irrelevant details such as 5 of the chosen kiwis were smaller than average, the LLMs saw accuracy drops of up to 65.7%, demonstrating their great difficulty in ignoring superficial information. These results highlight a fundamental limitation. AI models tend to convert any perceived detail into a mathematical operation, even when no such operation is necessary. For example, when tackling the kiwi fruit problem, many LLMs subtracted the smaller fruits from the total, suggesting that they had identified similar examples in their training that involved subtraction. This reveals a core problem. The models do not actually understand the meaning of the operations they perform, but merely imitate patterns they have found in the data. While these flaws aren't entirely new to the research community, the study reinforces how fragile LLMs are in their ability to handle situations that don't perfectly match the data they were trained on. Current AI models excel at generating convincing answers, but they lack a deep understanding of the reasoning behind those answers. As experts like Benj Edwards have noted, GPT-4's impressive performance is largely due to its access to massive volumes of data, allowing it to fool humans with answers that appear to be comprehensive but are actually sophisticated combinations of pre-existing concepts. This illusion of understanding is one of the biggest challenges facing modern AI. Models that appear to be reasoning can fail unexpectedly when faced with problems outside their training scope. AI expert Gary Marcus argues that the real breakthrough will come when these models can manipulate symbols and variables abstractly, as humans do in programming or algebra. Until then, LLMs will remain vulnerable to errors that a simple calculator would never make, limiting their effectiveness in applications that require robust, formal reasoning. Don't forget to subscribe to our channel, like the video, and share it with your friends. Your interactions mean a lot to us and help us grow. See you next time.